Hey there, welcome to Scripting for Artists. This is a video tutorial series on scripting in Blender. It is aimed at people who don't necessarily want to be a programmer, but for whom scripting may be beneficial. And it can be useful for a lot of things, as we'll see soon. Before we start, let me introduce myself. My name is Sybjørn Stuvell. I'm core Blender developer and I work at the Blender Institute, so I have experience working next to artists. I've worked on the Blender Cloud itself, and I've worked on Attract and Flamenco. I also have a PhD in computer animation, during which I worked on the Blender game engine, and after that I started working here at the Blender Institute. So about this series, it's about scripting Blender, basically letting Blender push its own buttons. If you've ever done any dumb monkey work that takes a lot of clicks and a lot of repetition, this may be the series for you. Examples where scripting would be useful are mass renaming of bones or objects, or rendering 10,000 OBJ files in some directory. One thing to keep in mind is that computers are stupid. They will just do what they're told line by line, word by word, and not really think about what you mean. So it's good to keep in mind that you have to be literal. So that's it for the introduction of this series. Let's go and do something practical in Blender itself. Blender can be programmed in Python, and that's quite a nice language that can be read and understood quite easily. Furthermore, it allows you to interactively toy around with it. So let's dive into Blender's Python console. Well, after I change my shirt, that is. So here is the default startup file. We can replace the timeline with the Python console because we don't need a timeline right now. Let's do some computations. 3 times 4 equals 12. 2 plus 3 times 4 equals 14, because multiplication and division go before addition and subtraction. So if you want to do the addition first, you have to use parentheses. 2 plus 3 times 4 equals 20. Let's go and see if we can do something to that default cube. If we press N in the viewport for the numerical data, you can see the locations X, Y, and Z. Let's move it somewhere else. So if you hover your mouse over the location, you can see some Python information. bpy.data.objects cube location 0, which basically means from Blender's Python interface, get the data in there or objects. From those objects I want to have cube. Cube has a location, and location has a few components. This is component 0, Y is component 1, and Z is component 2. So we can just copy this into our Blender Python console. bpy.data.objects cube .location 0, and that gives us the X location, and location 1 gives us the Y location, and of course 2 will give us the Z. Alternatively, you can use letters. So there is actually an .x, do exactly the same thing, and I like those a little bit better. It makes your script a bit easier to read if you just name them X, Y, and Z. This isn't limited to reading, we can also write to it, so we can set .z to 0. And then it's back at 0 or 1, or we can use plus equals, which means increment. So increment by 0.1, and we can keep using this. I'm pressing the up arrow key in the console. That gives me the previous command, and then press enter, so you don't have to type everything by hand again. We can also assign to the location directly instead of to each component individually, by removing the last component and then assigning it 3 numbers in parentheses. So for example, like this. And then we've set X, Y, and Z at the same time. This also works for scale. And it also works for the rotation. Except that on the Python side of things, rotations always work with radians and not with degrees as you might see in the user interface. So this might get a little bit getting used to. One more thing that may make things a little bit easier to type is that the Python console supports autocompletion. So you can do bpy.date and then press Ctrl space .ob. Cube you have to type yourself, but then rotation and then Euler. So this is done with Ctrl space. It can be really useful. It can also help you figuring out what is there to type in the first place. So there's a whole list of things here. These you can find in the documentation, by the way. If you go to help and then Python API reference, then you get all this information, but we'll cover that in a moment. Let's look at some other things we can find about Python in Blender's user interface. We have seen these properties of existing objects, so let's see if we can delete and maybe create some new objects. This is done with operators, and operators are Blender's way of binding certain functionality to menu items or buttons in the interface. So what we can do is just hover over a button and then you see the operator command. You don't even have to remember it. You can just press Ctrl+C to copy and then press Ctrl+V to paste it into the console and it will just work. So now we've deleted an object. Let's take a look at creating one. You can just press Shift-A, then over an operator, hover your mouse and you see bpy.ops.mesh.primitive-UV-sphere add. So again, press Ctrl+C and then in the console press Ctrl+V and enter. And there you have your sphere. It's a bit boring one, it's the default one. So let's see if we can do something about that. Don't be afraid if you don't understand all these options yet. I will give you some information later where you can find out exactly what they do. So let's create it with size equals 0.10 at location 1, 2, 3. And there you have a really tiny sphere. And let's create a bit bigger one at a different location. It's that simple, really. We've already found quite a bit of information in Blender's user interface, but there's also Blender's API documentation, which you can find right here in Blender, Python API reference. It opens the browser for you with the information. And you can use that copy-paste trick again. So let's see, Shift-A, Mesh, UV Sphere, I Ctrl+C, then I go to the browser and hit paste in the quick search. Click on the first link. And there you have the explanation of what is what. Another good source of information is the Python standard library. So what have we seen so far? Well, we know that computers are stupid and just do the commands one by one that we give them. We've seen how to use the Python console and how to create objects, remove objects, and modify existing ones. We've seen what we can do with just copying information from Blender's user interface. And I've pointed you to a few sources of information where you can find more stuff. So in the next video, we will look at names and objects, because typing bpy.data.objects.cube.something becomes really boring after a while. See you in the next video. Hello and welcome to video 2 of Scripting for Artists. This time we're going to talk about naming and objects. So names and objects, or what does that dot stand for? We've seen a lot of dotted things like bpy.data.objects. You have some object.location.x. We're going to take a look at that. So in Python, names refer to objects. And an object is pretty much anything. It's a thing in memory. It can be very complex, or it can be as simple as a number. So 4 is an object, but also your mesh is an object. Texture is an object, animation is an object, everything is an object. So names refer to objects, and that is pretty much how we use it in real life too. Say you have that ledge over there with that stack of monkeys, and then third one from the top, he is looking in a certain direction. Always talking about that monkey on that ledge, and then on that stack of monkeys, the third one from the top, gets tedious after a while. You wouldn't do that. You would give the monkey a name, like Steve. So now we can say Steve looks in a certain way, Steve is among 2 of his friends, and it's a much shorter way to talk about exactly the same monkey. And with Python objects, it works in pretty much the same way. You can have multiple ways of addressing the exact same thing. So we've seen this before, the bpy.data.objects monkey location.x, and say we want to call the monkey Steve. And we can do that. We can say Steve equals the monkey. So after we've typed this, those 2 lines are exactly the same. Steve.location.x equals minus 0.5, just assigns minus 0.5 to the x location. And the line below that does the same thing, but it's longer. This works until we assign something else to Steve. We can also say Steve equals 3, and then Steve.location.x equals something will fail because 3 doesn't have a location, it's just a number. This is a type of error that Python will give you if you attempt this. It tries to get the location of Steve, but Steve is just number 3, so it doesn't have a location. And location is called an attribute, so that's why you get an attribute error. Int object has no attribute location. Int stands for integer, which means a whole number. And at the moment, that is the type of object Steve refers to. 3 is a whole number. We'll talk about types in a future video. A good thing to realize is that you can have multiple names for the same object. We've already seen Steve, and we have bpy.data.objects monkey. And those are 2 names for the same object, but it's not limited to that. So let's go to Blender. Here we have Steve equals bpy.data.objects monkey, and Steve has a location. But we can also say Alan equals bpy.data.objects monkey. And Alan also has a location because it's the same object. It's still the same thing in memory, it's the same monkey. And if we say alan.location.x plus equals 0.1, we see a monkey moving. And if we do the same thing with Steve, it is exactly the same monkey. The names Alan and Steve thus refer to the same object, and this concept of having multiple names that refer to the same object gives rise to Blender's context. And this is a very useful thing. It's a special object that gives you names for the context, the current state of Blender. So it has .activeObject for the current active object. It has .selectedObjects, which is a list of all selected objects. The current scene is .scene, the selected postbones are .selected postbones. And we can take a look at that here in the console. bpy.context and then control space, and you can see this whole list of things you can use. So you can see that we can keep dotting. We got bpy.context.activeObject.name, and that is at this point the end of it, or is it? Well, it's not. Name is a string. It's a collection of characters, and you can convert them to uppercase, lowercase, pick the first character out of the bunch. But we'll get to that in a later video. So these dots are some sort of hierarchy. Everything starts with the Blender Python interface, dot, and then you can do stuff like .app, control space, and there you can see version, which gives you the version number of Blender. So you can keep dotting and dotting and dotting. Another example is this one. It's a bit longer. So this looks at the active object and then at the collection of modifiers on that object. And that is something that you can index by number with the square brackets, or with a name also with the square brackets. Let's look at this in Blender itself. bpy.context.activeObject.modifiers skin. And this gives us an error because we haven't added the actual skin modifier yet. So it raises a key error saying key skin not found. And every time you use a string, like a name, something like this, between the brackets, it's called a key. So let's add the skin modifier. And now this gives us the modifier object. We can ask for its name or look at the branch smoothing. And this we can, of course, increase, and then you can see that here in the user interface as well. One of the things you may notice is that if you hover over this property, you can see that it says bpy.data.objectsCube.modifiers blah blah blah. Whereas what we changed was something else. It was bpy.context.activeObject.modifiers blah blah blah. And this shows that bpy.data.objectsCube at this moment in time refers to the same object as bpy.context.activeObject. And that is, of course, because it's currently our active object. If we select the camera and try to do the same thing again, of course we get that same key error because the camera doesn't have a skin modifier. So I hope this example makes it a little bit clearer how you can access the same object under different names, and different names mean different things at different times. You may have seen in the console that it says capital C equals bpy.context. That is shown here at the top. Convenience variables C equals bpy.context. And that means that instead of typing bpy.context in the console, we could have also typed capital C. It's just a different name for the same thing. This means that in the console, capital C is the same as bpy.context, so you can say capital C.activeObject, which is the same as bpy.context.activeObject, But do know that this capital C is a utility, is a useful thing that was given to you by the console. So you can't readily use it in your own script unless you also say capital C equals bpy.context. So we've reached the end of our video. To recap, we've seen that everything in Python is an object. We know that names refer to objects and that you can have multiple names to refer to the same object. We've looked at the context and seen that there's quite a bit of useful stuff in there. We will look more into this into the next video. And we've seen that we can use dots to dig through names and objects. Don't forget to use control space for auto-completion. So the next video is all about stuff on lists, and then we go dive into a more practical application. Hello and welcome to video 3 of Scripting for Artists. My name is Sibrin, and today we're going to talk about stuff on lists. So there is a lot of things that are in lists. You can have the selected objects, which is a list. You can have a number of files you need to import and render, which is also a list. Before we begin, I want to explain a little bit of terminology. We'll be talking about looping over a list, and that is the same as iterating over a list. It means looking at the list and then visiting each thing in there one by one in the same order that they are in the list. So having said that, let's dive into our first example code. For ob in bpy.context.selectedObjects, print ob.name. bpy.context.selectedObjects, we've seen this one before. It's the list of currently selected objects. And the for loop gives us the ability to iterate over all these objects in this list. The indented part, which is currently just one line, the print line, that is the part that will be repeated over and over again for everything in the list that you give to the for command. The first time around, ob refers to the first thing in the list, and the second time round ob will be referring to the second thing in that list until that list has been run through. So let's see this in action. Here we are in Blender, and as usual we discard the timeline and turn it into a Python console, and then I will just copy paste that code into here. You can see that the prompt changes from 3 arrows to 3 dots, which means that Python understands that after a colon you need to indent it a bit, and it gives you a visual indication of that. So let's execute this. It doesn't execute yet because we haven't finished the indented block. Python doesn't know that this is the last line we want to type, so to let it know we're done we have to type an empty line. And there you have it. I only have one selected cube, so it prints the name of that selected cube. Now if we select a few more and do arrow up, up, enter, down, enter, enter, and there we have the 3 object names that we selected. If we look at that second line, it says print ob.name, and that is a function call. A function is basically a bit of code that has a name. In this case the name is print. A function can also take one or more input parameters, and it can do something and then optionally return a value. In this case the function is called print, and whatever you give it as parameters will be printed to the screen. Let's look at some examples. Print by itself will just tell you that it's the built-in function print. In order to call it, that is execute the code with that name, you have to use these parentheses. So print parentheses open close will just print nothing. You can give it multiple parameters, 1, 2, 3, 4, we'll print 1, 2, 3, 4. Print hello bye, we'll print hello bye, and print bpy.context.activeObject.name will print cube. Here you also see the difference between with and without these quotes. The quotation marks indicate that you mean the literal text. So if I do this with the quotation mark, it will just tell me bpy.context.activeObject.name, because that is the text that I give to it, also known as a string, because it's a string of characters. If I remove the quotation marks again, you can see that Python understands we mean the name of an object. When looping over things, we're not limited to just printing something. We can also manipulate something. We can say, of all the selected objects, I want the name to be converted to uppercase. And again, we have a function call that you can recognize by having a name and then 2 parentheses. In this case, the function is upper, which is a function that's defined on a string. And since op.name is a string, we can call .upper on it. So let's see what that does. We can have a string, so say name equals some name, and then name.upper returns some name in uppercase. And name itself is unchanged. And this is an important thing to remember. A string cannot change in Python. Some name is always some name. That string will not change in exactly the same way as 3 will never become 4. If we want to change the name of an object, that means we have to do two things. We have to calculate the new name, and then we have to assign it to the object. We can do that in one line, as shown here. op.name.upper calls the upper function on op.name, and then we can assign that as a value to op.name. So here it will assign a new name to all the selected objects. So let's see if we can do that. I have still the same 3 selected. Then I type this, enter. You can see that it automatically indents it for me. And then op.name equals op.name.upper. And then you see nothing on screen happening because we didn't print anything, so it doesn't output anything. And that's a general case with programming. If it doesn't tell you anything, usually that means a good thing. And here in the outliner we can already see that the 3 objects that we selected have changed name, and the other ones did not. So that's how you do stuff on selected objects. Let's say we want to select all objects that are hidden and that have .00 in the name. So something like cube.005. And this becomes a bit larger script, so we'll just go through it line by line. If you're typing along with me, you may want to open the scripting screen. This is already set up for scripting with your 3D view, your Python console, and a text editor. And that text editor is what we will be using from now on. So click on New. Text is a bit generic, so let's say something.py. It's always nice to indicate that it's a Python script by ending it with .py. This button will be important soon. Here in the Python console you see a lot of things. The built-in modules, the convenience imports, the convenience variables. If you don't know exactly what that means, it doesn't really matter. Just know that the console already sets up certain things that you usually don't get in your Python script itself. In order to use bpy, bpy.anything, we have to type import bpy first. You don't have to know exactly what it does, just know that it makes the name bpy available to you. So that explains this first line. Then it's always good to add a comment. Comment is something that starts with a hash mark or a pound mark or however you call it. And that is simply ignored by Python itself. It's just for you or for other programmers that read your code. And make sure that it's understandable. It's very important because you in a month or two will probably have forgotten what that script does. So a little bit of explanation of why you've done things in the way that you do, that will go a long way in the longevity of your script. So let's start by deselecting everything that was selected before, because the sort of output of our program is that certain objects get selected. So not to confuse previously selected with newly selected, we will just deselect everything. Then, we've seen the for loop before. We want to loop over something else though. And this is bpy.context.scene.objects, which gives us all the objects that are in the current scene. If the object is not hidden, we're not interested because we wanted to select all hidden objects. So usually it's a good idea to check for things that you're not interested in and then say continue. That continue statement here, that will tell Python that you no longer want to run this iteration of this loop and that you want to go to the next iteration. So that means that this object is done. Let's go to the next object in bpy.context.scene.objects. After that, we're only interested in things that have .00 in the name. You can easily check this with the in operator. It optionally takes a not, so it pretty much reads like English. If the string .00 is not in op.name, we also continue. We're not interested in it. And then finally we get to actually doing your stuff. So I want to select it, so op.select equals true, and I also want to unhide it so that we can see that it was actually selected, so op.hide equals false. These attributes .hide and .select and .name, you can find them in the API documentation of Blender. And you can also find them by using Ctrl space in the Python console. I want to show you one more thing in the manual, and here you see object, and this is the Blender object documentation. So this has an active material, it has an active shape key, a bounding box. These are all the attributes on object that you can use in your Python script. Just know that everything that is defined on a base class is also available on the class itself. That might sound complex, but it's quite simple really. We have all the things here that are specific to objects, and if we go all the way down, you see here inherited properties and inherited functions. Again, you don't have to know all the technical details, just know that everything that's inherited is also available to you. Back to our script, let's zoom out a bit so we see everything and just run it. Click Run Script, and there you go, we have selected a bunch of cubes there in the background. Let's zoom in and see what they are. Cube 0, 0, 1, 2, 3, 7, 9, and of course the ones in between as well. So these are exactly the ones we were looking for. Let's hide part of those and run the script again. And now you can see that it only selected and unhid the ones that were hidden before. So our script seems to work. Here you also see the convenience of running your script from the text editor instead of having to type everything by hand on the console all the time. Let's go do something more elaborate, and scripting is especially useful for the boring monkey work. So let's do monkey work. Let's create 600 tiny monkeys. This is the code, and we'll go through it line by line. Import bpy is necessary, as we've seen before. We have a comment that tells us what we're going to do. And in this next line here, you see a different type of for loop than we've seen before. It loops over a range, and a range has a start point, which is by default 0, and an end point, which is in this case 600. And it ranges from the start, including the start, up to but not including the end point. In this case, it would loop from 0 all the way to 599. And we can do a little bit of math with that. So the x-coordinate we compute by taking idx% 25, and that doesn't mean 25% of that number. It means the modulo, which is the remainder after a division. So to give you an example, 7 modulo 4 equals 3, because 7 is 1 times 4 plus 3. Another example, 21%, let's pick 4 again, is 1. Because 21 is 5 times 4 plus 1. And this goes together with the double slash. This is an integer division. So I will show you what happens. 21 divided by 4 is 5 1/4. But 21 / 4 is just 5. It gives us the whole number division. Here you have it in a table. As IDX increases, you can see that IDX modulo 4 simply goes from 0 to 3 and then 0 to 3 again. And this makes it quite useful as an x-coordinate. And if we look at IDX divided by 4, you can see that it just increments at 1/4 of the speed of IDX, which gives us a good y-coordinate. Let's go back to our monkeys. We want 600 of them, so rows of 4 would be a bit narrow, so that's why we go up to 25. Now that we have our x and y coordinate, we can pass them to the operator. We pass them as the location parameter, and of course it's in 3-dimensional space, so we need to pass a z coordinate as well. We just pick 1. And we want to create a tiny monkey, so the radius equals 0.2. Let's make something new. Tiny monkeys.py. Paste it in there, and let's run it. It takes a while. And there it is, it's done. Let's find our monkeys. There you go. 600 tiny monkeys. You can see that the tiny monkey at the back is active, and that is because that just happens when you add something. If I add another monkey here, it is also active. So the last thing that was added by this operator is the active one. And that is very useful because that means we can do other operators after it, and it will operate on the thing it just created. Let's go see how that works. Let's create 600 tiny subdivided smooth monkeys. The first bit of code is exactly the same, And we will just have to add a few more operators. Let's see how we find them. Add a modifier, subdivision surface, again Ctrl C, and then Ctrl V in our code. And we wanted to shade smooth. Here, shading smooth, hover over it, Ctrl C, Ctrl V, and make sure that this indent is always the same. Before we run this, let's erase all the other monkeys that we have so that we can actually see where they are. Otherwise they would overlap at exactly the same coordinates as our previous ones. And run the script again. This will take a while because it not only has to create 600 monkeys, it also has to subsurf them, and then Blender also has to shade them smoothly. Just be glad you don't have to do this by hand. And there you have it, all the way up to Suzanne number 599. Let's take a closer look. A beautifully smooth and subdivided monkey. Before we go further, I want to have a look at the script that we looked at before, the very simple one that prints something. Let's see what happens if we put this into a text editor in Blender. We have selected Suzanne number 599, so we should see some name. But where did that go? I don't see anything here in the console. And that is because print statements only output to the Interactive Python console when they were given in the Interactive Python console. So where does it end up? Well, it goes to the terminal that you use to open Blender. You probably didn't use a terminal to open Blender though, and fortunately the Blender manual explains all that. You can find it in blender.org/manual, advanced command line introduction, and there for every major platform we have described how you go about opening the terminal. I will show you what this looks like in practice. So here we have Blender started from a terminal, and if I now run this script, you can see the output appear in the terminal. There is one very common pitfall that can occur when you're looping over a collection, and that is modifying that same collection while you're looping over it. So that means that you shouldn't deselect if you're looping over all selected objects, because that modifies the selected object selection. Let's look at an example that makes this mistake and then fix it. Let's say we want to deselect all selected objects that have .00 in their name. The start is pretty much what we've seen before. We have a for loop that loops over all selected objects. And if .00 is not in op.name, we continue, which is also fine. And then we say op.select equals false. And this is bad, because this removes an object from selected objects, thus modifying the list and confusing Python. Let's see an approach that does work. So instead of immediately deselecting when we find an object to deselect, we just need to remember which ones to deselect. And this we can do with a list. We can construct a list ourselves as well. We create an empty list, which you can do with bracket open, bracket close. You can also create a list with things already in there. I can give you a small example. You do that by putting them in between those brackets. So you can create a list of 1, 2, and 3, which gives you the list of 1, 2, and 3. And you can say L equals 1, 2, 3, and then L refers to that list. You can append a 4 to it, and then L includes a 4. You can append a 4 to it a lot of times. And then L has a lot of 4s. Back to our code. We still keep the same for loop because we wanted to loop over all selected objects. There's no other way we can do that, and the loop itself wasn't a problem really. The condition wasn't a problem. But then instead of immediately deselecting it, we just append ob to our list. Ob refers to an object in pretty much the same way as we've seen before. Steve refers to a monkey. And when we add a reference like that to a list, it basically means that we don't call it Steve, we just call it to deselect 0, or 1, or 2, or 3, depending how long that list is. But in effect, it's still a reference to that same monkey. So we remember which object passed our criteria. And then we have another loop that loops over all these objects that we remembered and calls op.select equals false. And this works because in both loops we don't change what we're looping over. I can recommend looking through the Python documentation for lists because it contains all the operators that are possible, all the function calls you can do on it, and it contains some more examples that you can look at. The for and if statements are called flow control statements because they control the flow of execution through a program. They can make certain parts execute depending on certain conditions, or they can repeat it, or they can prevent execution from certain parts. And there are many more. There's while, break, there's a else, if, and an else clause for that if we've seen. So there's more documentation for that at the Python tutorial. Is quite easy to follow, so I can recommend looking through it. And that already brings us to the end of our video. So to look back, we've looked at looping with for something in something else, including the continue statement that can skip part of the loop body. We've looked at calling functions like print or upper for strings. We have looked at conditionally running code with an if statement, created 600 tiny, smoothly shaded, subdivided monkeys, and learned a bit of math to put them in their spot. And we've worked with lists and added stuff to lists and looped over lists, and also looked at how to avoid biting yourself in the list. So that is the end. Thank you very much for watching this video. See you in the next video, which will be about data types. See you then. Hello and welcome to another episode of Scripting for Artists. My name is Sybjørn Stubel, and this video will be about data types. As we've discussed in a previous video, in Python, names refer to objects. Objects can be anything from simple numbers like 4, a name like Steve, or more complex things like a full mesh or the location of a lamp. As you can imagine, these things behave quite differently and have different possibilities in Python, and all these behaviors and possibilities are determined by their type, and this video is all about types. So certain types you may encounter, and we've seen already, are the numerical ones. There's int and float. Int stands for integer, which means a whole number. So that's 1, 2, 3, 4, 5, minus 7, etc. And float stands for floating point, which is a decimal number, so 3.5 for example. Float stands for floating point, which is the counterpart of a fixed point notation. And with fixed point you have a fixed number of decimals behind the comma, and with floats you don't, it's variable. So that can be anything from 10 to 10.000001. The most basic type is the Boolean, which just represents true or false. So any outcome of a comparison, say x bigger than 5, is a Boolean. Also, operators like in, like we've seen with strings, return a Boolean, and that's the thing you can use when you're using an if statement. Another type that we've seen before is the string. It's a sequence of characters, so that's why they call it a string, because you string different characters together. Another object that is very special is the none type, and this is a special object that literally denotes nothing. Maybe you've seen this already when you access bpy.context.activeObject without any object being active. In this case, the value of the property is none. Let's look at an example. Here we have the default cube selected, and it's the active object. If we delete it, there is no more active object, and it's now none. Python doesn't even show this because it's really nothing. Other types that you will encounter are Blender-specific ones, like object and lamp and camera, mesh, that sort of thing. And then there are the Blender math types, which are vector, matrix, Euler, and some other ones. And you've also seen a little bit of these. For example, the location of an object is a vector. And then there are the collections, so they contain multiple values. And there are lists, digs, sets, and other types. And we'll look at that in more detail in the next video. As I said, type determines behavior. So let's look at some examples. Here I just multiply 3 with something else, and let's see what happens. 3 times 3 equals 9. If you multiply two integers, the result is also an integer. If I multiply 3 by 3.0, then I multiply an integer with a float. And that returns a float. As a rule of thumb, Python tries to keep the precision the highest. So if you're multiplying with something that has digits behind the comma, then the result will always be a float. Same goes for addition and multiplication, division, everything. We can also multiply a string. So if I do 3 times the character x, then you get 3 x's. And this works for words as well. In the last example, you can see what happens when two objects are not compatible with each other. So 3 times the active object doesn't really make sense, and Python tells you in this way with a type error. So you can see that the first object that you tried to multiply was of type int, and the second one was of type object. And object with a capital O here means an actual Blender object. As for other numerical operations, Python does pretty much the same thing as you've probably learned at school. The notation might be slightly different, so it's a slash for division, it's a star for multiplication, and it's a double star for the power of. So 2 double star 5 means 2 to the power of 5. The cool thing about Blender is that you can actually use these operations in Blender's user interface itself for all the numerical inputs. Let's look at an example. Let's say I want to change this resolution from Full HD to a 4K. So that means that it is 2024 times 4, and then here I can say 4096 divided by 16 times 9, and there I have my vertical resolution as well. This of course also works for location, so if I want to have this cube 2/3 up, then I can just type 2 divided by 3, and there it is. When it comes to strings, there's also a couple of things that we can do. A string can be defined simply by typing it between quotes and assigning it to a name. You can access individual characters in the string with a bracket notation, and that starts counting at 0. Another way to access the string is by slice, and that gives you a subset of the string. So in this case it's the index of the first character that you want, colon, and then the index of the first character that you don't want anymore. So it's from 1 up to but not including 3. Either of these numbers is optional, so you can take everything up to but not including character number 6, and you can take everything from -4 to the end. So what's that? Well, minus means just count from the end, so it's the 4th last character up to the last one. Lists we've seen before, and these are just lists of anything. In this case we have a list of strings, but you can put anything you want in a list. It doesn't even have to be objects of the same type. You could mix strings with ints and floats and other things. Usually this is not a good idea though, and it may be an indication that you need to think about the structure of your script. As you can see, the notation for lists and for strings are pretty much the same. You have these bracketed indices, and you can also take slices. And this is because they are basically the same thing in a very broad sense of the word. Whereas strings are lists of characters, lists are lists of objects. So that is why you have a similar notation. As you can see with the slice notation, you can go beyond the end of the list without any problems. This can be very useful in a script. These were the most common built-in Python types. Let's look at some of the mathematical types in Blender. So the vector we've seen a lot before. It represents a point in space. A vector is often three-dimensional, like locations in space or the scale of an object, because we're working in the three-dimensional editor. So it consists of 3 numbers, x, y, and z. But there's also two-dimensional vectors, like the control points in F-curves. And there's also a 1D vector, but usually we just call that a number. In Blender, for example, you can see a vector when you take the location of an active object. Here it is 0. And if you move it around, you can just see that the vector changed. This is also the thing we accessed with the .x, y, and z, because these are attributes of the vector type. When it comes to operations, then vectors work pretty much like numbers. You can add them together, you can subtract them, and you can even multiply them with an int or a float, and then it just multiplies the 3 different components. In the Blender API manual, things are a little bit more complex because not all the vectors are named such. If you look here, for example, at object.delta location, it says float array of 3 items. Usually that means that you get a 3-dimensional vector there in Python. If you really want to know what's what, just type it into the Python console and you can see it yourself. That already brings us to the end of this video. So to recap, we've seen that all Python objects have a type, and that that type determines the behavior of the object and the operations you can perform on it. We've seen some standard Python types like numbers and strings and lists, and we've also looked at a very common Blender math utils type called vector. So next video will be about collections. We'll look more detailed into lists and dicts and other useful stuff. See you then. Hello and welcome to another video of Scripting for Artists. I am Sybren and this video is going to be about collections. Roughly speaking, collections are things that can contain other things, and you've seen examples already, like the objects in a blend file or the selected objects, files on disk, vertices in a mesh. These could all be considered collections. In a previous video, we used a list to keep track of which objects we wanted to deselect. So in our example, Steve was no longer called Steve, but to deselect 0. That means that this whole stack of monkeys would be called to deselect. So in this case, Steve would no longer be called Steve, but to deselect 0. And that means that to deselect itself is a reference to a list object, and thus refers to all the monkeys in there. So far, nothing new here. We know that we can loop over items in a collection, and we can do stuff with that. And we've also seen that we can use collections to store things for us, so that we can look them up later. So in this video, we're going to look more into these two approaches. We'll be diving into another example, and this time it's about mass renaming of objects. I've seen questions like this before on the Stack Exchange site for Blender. People often want to mass rename things like objects, bones in an armature, vertex groups, etc. This can be for correcting mistakes, but can also be used if you want to change name scheme. Here we have some situation where we have right-handed things and left-handed things, and the right-handed things start with R underscore and the left-handed things start with L underscore, and we want to move the L and the R and the underscores to the end of the name. So let's see how we approach this, and it's always a good idea to think a little bit about your approach before you start coding, because it will make your code a bit easier to work with. First of all, we want to go through all objects. We would like to have only the ones we're interested in, so only with L underscore or R underscore in the beginning, but Blender doesn't readily give this to us, so we have to filter it out ourselves. So we go through all of the objects and we do something for each object, which is if the name starts with an R underscore, we rename it to something underscore R, and the same with if the name is L underscore something, we rename it to something underscore L. And these are really the only things that need to be done. Here we have the script. We will go through it line by line again. So we start with import bpy as we're used to, and then we have a slightly different for loop than we've seen before. Instead of looping over selected objects, we loop over all of them. And the bpy.data.objects collection has a little bit of a different structure. It is not like a list, but like a dictionary. And a dictionary consists of key-value pairs. So you can call .keys to iterate over all keys, you can call .value to iterate over all values, and .items will give you the items, which is the key and value pairs in one go. In our case, the key is the name of the object and the value is the object itself. Of course, we could have also looped over the objects only and use ob.name everywhere, but I just wanted to show you a slightly different way of going about things. The next line is an if statement, and we've seen parts of this before in the previous video. Name is a string, and name bracket colon to bracket indicates the first two characters in that string. So if the first two characters are equal to the string R underscore, we execute the indented bit on the next line. Else, so in other cases, if the first two characters in the name are equal to L underscore, then we execute the last line in the script. So that is roughly the structure. Each fully indented line, ob.name equals something, computes the new name. So it takes the name starting from character 2 to the end, and then appends underscore R if it started with R underscore, or it appends underscore L if it started with L underscore. This code works, but I'm not really satisfied with it yet. There are two things about this code that I don't really like. The number 2 appears in 4 different spots, and the relationship between those 2's is not really clear. Furthermore, the code for the left and right cases are pretty identical. We can extract that into a function and remove that code duplication. Here is the improved version, and you can see that the number 2 has gone altogether. Instead of getting the first 2 characters from name and then comparing that to R underscore or L underscore, I call starts with on the name. This returns true when the name starts with a given string and false otherwise. As a result, we can change the length of a prefix without having to change any other code. Another difference is that we change the way we rename the objects. So instead of computing the new name directly, we call function rename, which gets the old name and the new prefix we want, and then it returns the new name. This function doesn't exist yet, so let's look at how to define one. Here you have it. A function definition starts with the word def. and then you get the name of the function, and between parentheses the parameters that you want to use as input. And just like with an if or with a for loop that you've seen before, it ends in a colon and then an indented bit, and the indented bit that defines the body of the function. Next you see a triply quoted string, which is called a docstring, and it explains a little bit about what the function does, what it returns. I can really recommend writing these because they help you figure out what you want to do. You can give a little bit of a human readable description, and when you're writing a function and you notice that you're doing things that don't match that description, you know that you should either branch out to a different function and write your stuff there, or you need to redefine what this function should be doing. So while writing your script, it can actually help you focus. On the line below that, you can see that we removed another of those twos that I didn't really like. Instead, we just take the length of that suffix string that you passed, which is also 2. Actually, that 2 came from the length of the suffix. And in this way, our code represents that. Len is a built-in Python function, so you can always use that. And it will return the length of whatever collection is given to it. So a string is sometimes also considered a collection because it's a collection of characters. Len also works on lists and on dictionaries and on sets and all kinds of other collections. So now that we know the length of the suffix, we can strip off those characters from the front, which we do by some name, bracket open, sufflen, colon, and then bracket close, and add the suffix with a plus sign. And here you can see that you don't necessarily need to have a constant like 2, but you can also use a variable like sufflen. Note that there is an assumption in this code. It assumes that the number of characters that have to be removed from the start of the string are as many as we append to the end of the string. In our case this is correct, but it may be a good idea to document this assumption somewhere, say in that docstring over here. It's always a good thing to be aware of the assumptions that you're making while writing the code. So after you're done writing and it works, have a read through again and document which assumptions you made. You can just put them into comments, and that way you can find them again when you ever look back to your code and try to figure out what's happening. Now let's look what happens in this code. So let's say we have one object in our scene which is called r_Steve. And then name will be r_Steve and op will refer to the actual Blender object. Now if name dot starts with r_ will be true, this function will be called. And name is r_Steve, which means that when the computer starts executing this bit of code, some name will refer to that same string, so that will also be r_Steve, and suffix will get the value of the constant we define here. So suffix will be the string _r. Len suffix will return 2. Some name sufflen colon will evaluate to Steve, and then we add the suffix. What is returned here is Steve_r, which is exactly what we wanted to have. The flow of execution through a function will stop the first time a return statement is actually executed. A function doesn't necessarily have to have a return statement. In that case, it will end when it just flows out of the function. And it will return none. So a function always returns something, even if it's none. The return value that is determined here will then be the value of this expression, and that will be assigned to op.name. So in our case, the object will be named Steve_r, exactly as we want it to be. Let's say you've written this code and you've tested it on a couple of objects and it seems to work and you're happy with it. Then it's a good time to look back critically and read through it again. Usually you can find a few things to fix that won't take much time, but do improve the quality of your code. Looking back through the code we have so far, I think it's pretty good, except that I'm not too happy with the name rename. The actual renaming of the object is done by the caller of the function, so it's better not to put that into the name. So I think that this little change will actually fix things. The function now is called prefix to suffix, which matches what it's doing. Let's take it one step further and look at a more complex problem. Say we not only want to rename, but we also want to flip sides, so left becomes right and right becomes left. With just names, this would be easy. You would only change the _r and the _l suffix, swap them around, and you're done. So let's also look at our location in 3D space. We need to change the coordinates, and we'll just flip the x coordinate from left to right and from right to left. Of course, you can hardcode this directly, but this is a video about collections, so let's see which collection we can use. Let's say we've moved our prefixes to suffixes, so that is done. But now we also want to flip them. We want to take the existing suffix and map left to right and right to left. And to make it a little bit more complex, we also want to change the location of the object in 3D space. So let's flip them over the x-axis. Now let's dive straight into the code and see what it looks like. Here we define a dictionary, suffix translations, and this is done with the curly braces, and within these curly braces you have the key, colon, the value, and then a comma, and then another key value pair and another key value pair until you have built up your dictionary. On the next line I give to the name sufflen, and this is to make sure that it's clear that we're talking about a suffix length. You could be writing a script that moves objects around, and then you could have 2 meters between each object, and that could be the reason you have a 2 there. So to make it clear which 2 we're talking about and that each occurrence of that 2 is actually the suffix length, we just give it a name and use the name instead. Next we have a for loop that loops over all the objects, and then for every object we start by extracting the suffix from the name by counting sufflen characters from the end. If you look through the code a bit, you can see that sufflen is only used as a negative number. And strictly speaking, we could say sufflen equals -2 and then everywhere just use sufflen instead of minus sufflen. This would save a bit on the number of minuses that we have in our code, but I think it wouldn't make things clearer. As it is now, you can clearly see that we count from the back because every time we use sufflen we have a minus there. So it's really explicit in what it does. Furthermore, sufflen represents the length of something, which is always a positive number. So assigning a negative number just feels wrong. Let's sidestep the example a little bit and look more into the dictionary. Let's say we have suffix translations defined. Then suffix translations _r, written like this, returns _l, because that is what it maps to. And suffix translations _l returns _r. Of course, you don't necessarily have to do _l or _r. You can also give it something else like nope, not here. And that will raise a key error because that key doesn't exist in a dict. So we can say suffix translations nope, not here equals 47, and then it does exist with the value 47. And also nope, not here in suffix translations will return true because now it exists. Before it would have returned false. As you can see, the in operator doesn't only work for strings, but it also works for collections in general. In this case, it checks whether the given suffix is actually contained in our dictionary. Now that you know this, we can look at the code some more. The new suffix we look up from the suffix translations table, and that basically does this translation. Then we determine a new name for the object by stripping off the old suffix and appending a new one. The code is getting there, and if the name ends in _l or _r, it actually works. But of course, not all object names will end in this. So let's look back at our code and specifically at this line. If the last 2 characters of the name are not in our translations table, then this will cause a key error. To avoid this, we can simply use the in operator to check the suffix, like this. Now our code only operates on objects that have been marked with a left or right, and other ones are left untouched. So that takes care of the name, and then we have to multiply the x-coordinate by -1 to flip it by saying op.location.x times equals -1, which means modify the x-coordinate by multiplying it by -1. I think the code looks pretty reasonable, so let's see if it works. I've prepared a blend file here. We have Steven in the middle, and then Alan on the left, and Bill on the left, and we have Sandy on the right, and here Jimmy on the right. So here is the code, and let's see what happens if we run it. There you have it, everybody is swapped. So Jimmy right became Jimmy left, Sandy right became Sandy left, Steven is still unchanged in the middle, and Alan and Bill have moved to the right. And also the suffix in their name has changed accordingly. Now this works, but it has a downside. It will mess up a little bit. So if you have LNL and LNR, it may not go exactly as planned. This is because Blender tries to keep names of objects unique. And so you can have only one LNR and only one LNL. Blender will keep this unique naming in check even while your script is running. So let's see what happens if we rename something to a name that already exists. So here we have Sandy L. Let's rename Bill R to Sandy L in code and see what happens. So this is Bill R. And what you can see that because there is already an object named Sandy L, the new name is not Sandy L even though we assigned that to it, but it becomes Sandy L.001. If this is okay to you, then that's good. If not, then I'm sure you can think of a solution. I will leave this as an exercise for you guys. The key lies in producing another dictionary. one that maps the object itself to the new name it should get when all the renaming is done. You can construct this dictionary while you're doing the renaming, and then once that loop is done, once this one is done, you can create another loop over that new dictionary you created, and then give the objects their final name. If you can't figure this out by yourself, no worries, leave me a comment and I will give you a code example. But I don't include it here in the video just to give everybody a chance to think of this themselves. Okay, so the code works reasonably well and I'm quite satisfied with it. There are two things that still nag me a little bit though. What we do with the name is we cut it up into two parts. We take the suffix and we take the name up to the suffix. But these two things are actually in two different bits of code. Here we take the suffix and here we take the rest of the name. And I like those two together because it's part of conceptually the same operation. We split the name into two parts. Furthermore, I don't really like constructions like this. This is a construction like, if the situation is good, then we do it. This looks like a natural construct and it's also a way we think about these projects, but in structure of code it can lead to a lot of indents, and we'll take a look at that too. For now, we will just take the same approach as we did before, and that is looking at if it's not interesting and then use the continue keyword to skip the rest of the loop. So here you have it. The old code was on the left, the new code is on the right. Here we have that splitting up of the name, and you can see the symmetry here between up to but not including the suffix and from the suffix onward. And with these commas you can assign to multiple things at once. So you can do a comma b equals something comma something, and then you assign to a and b at the same time. The other change that you can see is that we've swapped the condition around. So instead of if suffix in suffix translations, we use if suffix not in suffix translations. And then we continue, and this removes an indentation level from a majority of the code. I like it that way. I like the code that actually does something in the for loop to be separated from the code that checks whether we have to do something or not. This is also more extensible. Imagine that we have another condition that we have to adhere to. Let's say we only want to do this swapping for all the objects that are above the ground level. So then you get another condition. If op.location.z is bigger than 0, then we do it. And you can see that by adding that one more condition, the rest of the code is indented by another step, and if you add another condition, it's indented even more, and that means that you're pushing it further and further to the right. Instead, if you use my approach and check for things you don't want and then immediately continue, it doesn't indent anything anymore. So that means that the code that does the core of what needs to be done, namely renaming things and swapping the location, is still there in the same spot it was, even though we added another check. By the way, this a comma b equals something comma something construct, you can also use that to return multiple return values from a function. I will give a small example for that. Let's say you have a function called plus minus. That takes an a and a b, and it returns a plus b, comma a minus b. Now let's see what happens when we call it. Plus minus 5 and 11 gives us 16 and minus 6. And we can assign this to a comma b equals plus minus 5 comma 11, and then a is 16 and b is minus 6. We can also assign this to one value. Let's say c equals plus minus 5 and 11, and then c contains both numbers. And we can use c0 to get 16 and c1 to get minus 6. This kind of object is called a tuple. It's like a list, but not quite. If you want to know more, I can recommend looking it up in the Python manual. Blender uses Python 3.5 at the moment and will be switching to 3.6 pretty soon, so make sure that the Python tutorials or documentation that you're referring to actually are about Python 3. And that brings us to the end of this video. To recap, we have looked at dicts and how to use them. They're a very powerful tool, and Python's dictionary implementation is really efficient. Furthermore, we've looked at creating our own functions and returning not only one but even multiple return values. And we've also looked at a few ways you can restructure your code after you've got it working, just to give it that little extra. And finally, we've looked at tuples as a way to quickly assign multiple references to multiple names, or to return multiple return values with one return statement. The next video will be the first in a series of a bit more technical ones, where I discuss concrete problems that I've seen on Stack Exchange. In the upcoming one, I'll be looking at updating animation data with Python. See you then. Hello and welcome to Scripting for Artists. My name is Sibren and this video is the first in a short series in which I go through specific questions I found on blender.stackexchange.com. In this video we'll dive into the question about setting scale of a Z object to 0 for a complete movie. And here you have the question on Stack Overflow. If you want, you can pause the video here and read through it all. But in short, they have a lot of keyframes and one particular property has to be set to 0, in this case the Z scale. Of course, there's multiple ways to approach this. You could just delete the animation data for the Z scale and then set it to 0. But this wouldn't be scripting for artists if we wouldn't use a Python-based approach. You will be able to use this not only for scale, but also for location, rotation, any animation data in Blender. So we'll be looking at modifying existing keyframes. We're not adding. I think that at the end of this video, you'll be able to do that yourself as well with the help of the API documentation. So let's go to Blender and look at a concrete example. So here we have a simple animation of a bouncing Suzanne. It looks nice in 2D if you're not an animator, which I'm not. And if you look from the side, you can see that it's bouncing all over the place because the Y coordinate is completely off. So let's fix this by setting the Y to 0 for every frame. What you see here is that Suzanne has a Suzanne action. And the action contains all the F curves. So that is also what we have to look for in Python. So let's press F4 and go to the Python console and see what we can come up with. We know we have to get to Suzanne first, which was our active object. So we can go to c.activeObject. And then it has animation data, which has an action. And this is where you want to be. This is the action that we're actually looking at down here. So to make things easy, let's call this A. You would never use a name like A or F in your source code because you want to have it more descriptive. You want to optimize your script for readability and not necessarily for speed of writing. So in your scripts, always use longer names and simply say F curve or action instead of F or A. But here in the terminal it's fine because it's just less typing. Now that we have the action, let's look what's inside. Here you see that we have F curves, which is what we need. Every F curve has what is called a data path. This data path determines which property of the object is driven by the animation data in the F curve. And these names are closely related to what you see in Python. I'll show you how to get the data path in a moment. Now let's get back to the action's F curve property. This is a collection and you can index it as if it's a list. So there's 1, 2, 3, etc. This is nice if you want to take all F curves and iterate over them, but it's not so nice if you just want to have one particular F curve. Something that is easier is to call .find. This takes a data path and it takes an index. So how to find that data path? Well, it's pretty easy and Blender will tell you what it is. If you go to the properties panel, you can just right click on any property and then click on copy data path. This will give you location, but you can also take it from rotation, for example. Anything that can be animated has a data path. And then there's the index. So you can see that copying the data path of the Y location only gives you the word location. And that is because the location is a vector, so that's one thing. And then within that vector you have index 0, 1, and 2 for the X, Y, and Z coordinate. So since we want to have the Y coordinate, we pass index equals 1. And this gives us an F curve, so let's call that F. One thing you have to know about the fcurves.find function is that it goes through all the F curves one by one until it finds the one with the given name and index. In practice, this means that you want to do operations per F curve. So you take one F curve, you go through all the keyframes on that F curve, and then you find the next F curve to operate on, rather than finding each F curve again and again for every keyframe you want to handle. Before we go modifying the keyframes, let's look at evaluating the curve itself. You just call f.evaluate and then a frame number. And that gives you the value of the F curve at that point in time. And this gives you the ability to evaluate the value of a certain property on a specific frame without having to tell Blender to go to that particular frame. Since with a heavy rig character, switching between frames can be very slow, this can provide a massive speed up to your script. The keyframe points themselves are stored in the keyframe points property. And this is a list, so you have keyframe points 0, 1, etc. .co stores the coordinates in a 2D vector. And the first coordinate is the frame number and the second coordinate is the actual value at that frame number. Let's go to frame 1. As you can see, keyframe point number 0 corresponds to frame 1 with this value, which is what we see here in the user interface as well. And now we can set the Y coordinate equals 5 and you can see it jump up here. This .y comes from the y coordinate of that keyframe here. So that means that it's the value of the keyframe itself. It doesn't have anything to do with the fact that we are changing the y coordinate of the object. It's the f-curve that links to the location and then index 1, which means the y location. The f-curve could just as well influence the z scale, for example. And then if you want to change the value of a key point, you would still change .y, because that is the height of the keyframe point in your animation editor. You can see that Suzanne hasn't moved yet, and you can see that the property here is still the same. And that is because after changing an f-curve, you have to call update. After changing an f-curve, you always have to call its update function. This makes sure that Blender's internal administration is in order. You can see that Suzanne hasn't moved in the 3D viewport, and you can see that here the location is still not set to 5. Why is that? Well, that is an optimization. And this is a good thing. If Blender would update everything all the time, every time you change something, that would also make your script very slow. You can see that if you change frame, then Blender updates everything. So now we've seen how to get to the action of the active object, we have seen how to get to an f-curve given the action, we've seen how to get to the keyframe points given an f-curve, and we've seen how we can change those keyframes. So let's put this all into one big script that does this for all selected objects. So here you have it all in one script. This resets the y coordinate of all selected objects to 1 in this case. So let's go through it line by line. We start with import bpy. We define reset2 to be 1.0, and this is what the y coordinate will be reset to. As we've seen before in previous videos, we go through each selected object with a for loop. So now there are a couple of cases that we have to consider. For one, the object might not even be animated at all. In that case, Blender sets animation data to none. And the same goes for the action. If there is no current action selected, Blender will set that property to none as well. We check for this situation in this if statement. If there is no animation data or there is no action, we simply continue to the next selected object. So the object may not be animated at all. In that case, I thought it might be nice to have the y coordinate reset anyway, so that is why I start with object.location.y equals reset2. Every object has a location, every location has a y coordinate, so there's nothing special here. So once we know there is an action, we can go and get it, and given the action we can find the f-curve. By now the only thing that we know is that the object is animated, but it might not have an f-curve for the y coordinate. Maybe it was the scale that was animated or some other property on it. So in that case, when you call find with a data path that doesn't have an f-curve, find will return none. In this case there's nothing for us to do, so we can continue to the next object. And once all that is done, we can finally iterate over all keyframe points and fix their value. For every f-curve, Blender keeps some internal bookkeeping, and this needs to be updated once you change the keyframe values. So once you're done editing, call fcurve.update. And that is it. This goes through all selected objects, and if there are y-coordinate keyframe points set, it will reset it to whatever value you choose as reset2. So let's look at this script in Blender. If we run it, we can see that the y coordinate is set to 1.0. Here it's set as well. Suzanne moved, and if we play the animation, she neatly moves with a fixed y coordinate. We can take a small variation on this, and instead of setting it to a fixed value, we can set it to a random value. The only thing that I had to change was to import the random module to give us random numbers, and then call random.uniform -2, 2. For every call, this gives us a random number between -2 and 2. Let's look at this in Blender 2. We can run the script, and then you see that this green line here for the y coordinates gets nice and scribbly. And again and again and again, and if you hold Alt-P, you see this. Of course you can also do effects like this, like randomization. Of course you can do an approach like this with drivers as well, but this has a downside. For every frame change, that driver has to be executed again, and that can slow down Blender. And you also don't have much control over it, whereas with the technique in this video you have normal keyframes that you can go in and tweak if you want to. If you go to the Python API library and search for f-curve, there you find everything that we've seen before and more. Here you can see the keyframe points and their collection of keyframes. And there you can see that you can change the coordinates, which we've seen, but you can also change the easing, the handles, the interpolation style. So all the settings that you can change per keyframe and per f-curve in Blender's user interface, you can also set with Python and automate it. And that already brings us to the end of the video. To recap, we have seen how we can find actions and F-curves using control space. And we've evaluated F-curves without going to that frame for a major speed boost. We have adjusted existing keyframes from Python. And always remember to call fcurve.update once you're done editing an F-curve to make sure that everything in memory is also set up correctly. In the next video, we'll be looking at batch rendering 10,000 of OBJ files. See you then. Hello and welcome to Scripting for Artists. My name is Sybren, and in this video we will be looking at batch rendering of 10,000 OBJ files. As with the previous video, we'll be looking at a concrete example from the Stack Exchange website. Here, Phi asks the question how to render 10,000 wavefront OBJ files. He also notes in the comments that those files can be quite big. They can be up to 40 megabytes each, and that means that they can't all fit in memory at the same time. This means that we'll have to import, render, and then remove from memory every individual OBJ file. And this is very tedious work. Even though you can do it by hand, you don't really want to. Because the steps are all the same for each object, it's very easy to script this. So let's take a look at what's involved. First of all, let's ensure that we can actually import OBJ files. Blender's default settings come with this add-on enabled already. Just make sure that it's also enabled on your machine. Furthermore, we're going to render individual images, so make sure that your output is set to render actual images and not a video, because otherwise things will go wrong. And of course you can all do this in script, but usually it's just easier to set up your file and your scene by hand. So that means import one of the OBJ files or maybe two, set up a scene, set up a camera, make sure that the lighting is correct. Hit render a couple of times to see that it is actually what you want before running it on 10,000 OBJ files. So the approach is going to be find, load, render, and remove. We have to find the OBJ files. For each OBJ file we have to load it, we have to render it, and then we have to remove it from memory before loading the next one. So for that first step we have to find the OBJ files, and that means accessing the file system. I'm assuming here that all your OBJ files are in a single directory. There are multiple ways to access the file system, but I think the most convenient one is to use Python's pathlib library. I will link to the official documentation in the video description. So how does this work? Well, you call pathlib.path, and this creates a path object for you that is particular to your platform. So Linux and macOS all use the POSIX standard, which stands for the Portable Operating System Interface. Windows, on the other hand, does not use that. One warning to all Windows users: the backslash in Python strings is a special character. You don't have to understand all of this, just know that it's easier to just use forward slashes in your paths instead of backslashes, even when you're on Windows. Let's take a closer look at these path objects. Let's save some typing and give it a name, so let's call this path object P, and then you can go up the file system tree by calling p.parent, and of course you can also call .parent, and so on. This will give you the parent directory of a file or a directory. Of course you can also go down the tree, and then you can use slashes, so you can do p, slash, and then a string. So in this case it appends OBJ files to the path in a platform-independent way. So even when you've programmed this on Linux and you're executing it on Windows or vice versa, this style of programming will always work. You can use this for directories, but also for file names. Now some file is a path object that points to the file.obj, and now we can use the .control space combo again to figure out what we can do with such an object. Well, for example, you can get the name. So some file.name will just return the file name without any directory component. And we can break it down even further. We have the stem and the suffix. So this is quite useful, because then we can import the file.obj and we can get the file and use that to render to the file.png, for example. And this gives us a nice mapping from the OBJ file name to the final rendered file name on your disk. Unfortunately, not everything in Blender accepts path objects, so sometimes you will have to convert it to a string in order to pass it to operators. You can simply do this by calling str parentheses some file parentheses. And as you can see, this gives you the full path that you can then pass to Blender. So before we continue, I would recommend pausing the video now, going into Blender, into the Python console, and toying around with pathlib a little bit. Create some paths that do or do not exist in your file system, and use control space to explore these objects. This will give you a little bit more feeling of what we're about to do. Here we have the script in its full glory. We import bpy and the pathlib modules, then we create a path object for where we can find the OBJ files. If you typed along with this video, then you will have tried importing an OBJ file yourself by hand. And one thing you may notice is that after importing, all the objects that were imported are also selected. So this is important for us. Because we have to remove those objects from memory again, we have to be certain that everything that was selected was also imported. And the easiest way to do this is just by starting with a clean slate and deselecting everything. This next line works in conjunction with this line. So we'll come to that when we hit this line down here. The for loop loops over everything that's returned by obj_root.glob_star.obj. Glob is a slightly strangely named function that returns all the files that match a certain pattern. So in this case we can iterate over all the files that end in .obj. Now we get to the part that is executed for every individual OBJ file. So this will be done 10,000 times in the original case on Stack Exchange. First we start by importing the file, and this command you can find again in Blender's user interface. Go to File, Import OBJ, and there you have it in the Python tooltip. Ctrl-C, and then Ctrl-V in your code, or Ctrl-V in the search box for the Python API reference to figure out all the parameters that go in there. The only mandatory argument is the file path itself, and as I said before, we cannot pass a path object there, so we have to convert it to a string first. This loads the OBJ file, which may load one or more objects, and also selects these objects. Then we select the output file path, and this is also something that I took from Blender's interface. I want to have monkey.obj rendered and then written to obj_monkey.png. So let's take a look at Python's interface. Here in the output panel, you can hover and then you can see the data path again, bpy.data.scene.render.filepath. Well, rather than hard-coding the scene name in my Python script, we can also take the scene from bpy.context.scene. So this is what I've done here on this line. It takes the current scene and then its render property. And because this doesn't change while we're looping over these OBJ files, I took it out of the loop and just gave it a different name so that it's shorter, easier to read. And then here we construct a new file path to output to. Blender will already add the .png for us, so we don't have to type that here. And we just render to the renders directory relative to the current blend file, and then add obj- to the obj file name. As we've seen, taking the stem will just give you the name of the obj file without the .obj at the end, which is exactly what we want. After that we render the scene and tell Blender to write the resulting image file to disk. Fortunately, this render call is blocking, which means that the script will stop execution and it will only continue after the rendering is done. So when it continues, we can delete all selected objects because the ones that were imported were selected and the ones that were already in our scene were deselected. This means that by calling bpy.objects.delete, we only delete what was imported. So you can give this a try and see that it works. Well, does it? It has one problem. You will probably know that when you delete an object, the mesh still remains in memory. Here, I can show you. We have a cube here, I delete it, I add a monkey, and then here in the mesh panel you can still see that the cube is in memory with 0 users. Ordinarily this is not really a problem, but since we're loading 10,000 objects that do not all fit into memory, we have to solve this in our script. So here is the fixed version, and again a list comes to our rescue. We need a list here because there could have been multiple meshes imported from one file. Furthermore, we have an ordering issue. We want to remove the meshes, but we can only do that after the objects are no longer using them. And we know which meshes were imported because they were used by the objects that were selected. So first we have to know which meshes to delete, then we delete the objects, and then we delete the meshes themselves. Here we construct an empty list. Then for all selected objects we append object.data. And the .data property always contains the data of the object. So for a mesh object, that means it contains the mesh. For a curve object, it's the curve. For a text object, it's the text itself, etc. Once the loop is done, we have a list of meshes which later on we can delete. Then we delete the objects just like before. And then we can loop over our list of meshes to remove and actually remove them from the bpy.data.meshes collection. This thus solves our problem because it actually removes the meshes from Blender's memory. And that's it. We now have a memory efficient way of rendering 10,000 images from 10,000 OBJ files. One more flow control command I want to explain to you is the break command. In this case it's essential for getting your script right. Of course, while you're writing your script you want to test it, and you don't want to do this on your full collection of OBJ files. Usually, if the for loop runs correctly for one file, it will handle the other files as well. This is where the break command comes in. If you put it in a loop, Python will break out of that loop. So in this case, after handling the first file, it will break out of the loop and not even consider the second, third, etc. Once you're convinced that your script is doing the right thing, you can remove the break and rerun it to handle all your files. And this brings us to the end of the video. To recap, we've looked at the use of pathlib.path objects to define in which directory the OBJ files are and to actually find them. I've told you that the scene setup itself doesn't need scripting. Once you start working on scripts, you will know that you'll start to want to do everything with scripts. And sometimes it's just not practical. Sometimes doing things by hand is much easier. We've looked at memory efficient loading and rendering of objects. And we've looked at using the break command to break out of loops. In the next video, we'll be looking at mass renaming of bones. See you then. Hello and welcome to another video in scripting for artists. My name is Sybren and this video is all about mass renaming of bones. This question comes from somebody on Stack Exchange and they want to rename the bones and the vertex groups in a mesh. The problem is that they have an octopus and they created one leg with an armature and then duplicated that leg a couple of times to create the octopus itself. So now they have 6 leg meshes and 6 armatures, and of course the bones in each armature and the vertex groups in the mesh are all named the same. What they want to do is to rename the bones in such a way that they are unique, so that after the script is done, all the armatures can be merged and all the meshes can be merged without creating naming conflicts. In other words, what we want to do is to rename each bone to the name of the armature plus the original name of the bone. Here we have a blend file that I set up. As you can see, we have 6 armatures, 1 through 6, and every armature has a tentacle bottom, tentacle mid bottom, tentacle mid top, and tentacle top bones. And of course the meshes also have these 4 vertex groups. So our approach will be to loop over all selected armatures, then find the mesh that is actually using that particular armature, and rename all the bones and vertex groups. So the first bit is pretty simple. We import bpy and then for our armature in bpy.context.selectedObjects we do something. We have to select only armature objects, so we can do that with if arm.type is not equal to armature, continue to the next object. While writing the script, this is actually where I would start already executing it. It doesn't do anything useful yet. At least it enables you to print the name of the armature that you're looking at, and it also prints done. I often print done at the end of my scripts, and for a good reason. If there is a bug in my code, for example in this line, maybe it will always continue, and thus it will never actually get to this print here. As a result, without that last print, it wouldn't print anything. And now, when I see done on the terminal, at least I know my script ran, and I can investigate the situation further to see what was going wrong. To create this scene, I parented the armature object to the mesh object, and then chose automatic weights. This means that from the armature, we can go to the mesh that's using it by inspecting its children. So this is the next step of our script. Here we loop over all the children of the armature. In our situation, this will be only one object, but we don't have to know this. Just a for loop will work, and it will keep working even if the situation changes a bit. And then we have a choice. We can loop over all the bones in the armature, or we can loop over all the vertex groups in the mesh. Either way will work, so we'll just follow the approach given on Stack Exchange. So now we have all the ingredients that we need. We have the armature name, we have the vertex group name, and that gives us the ability to construct the new name for the vertex group and thus for the bone. When writing a script like this, I always take it slow. There are many for loops here, there's an if statement, we combine information from different objects. As a result, it's very easy to make a mistake. So rather than doing the renaming right now, I'd rather just print what we're going to do. By only printing what we're going to do, we can keep running this script without changing the situation. That means we can quickly edit and rerun until it's correct, and only then start working on actually changing the data. So running this script on the test file that I created will give this output. I have cropped the first lines a bit. You can see that it renames everything correctly by prepending the name of the armature. So now that we have a fairly good indication that the script will work, let's make it actually do something. arm.pose.bones will give us a collection of all the bones in the armature. We can key it by the bone name, which is identical to the vertex group name. Then we can rename the bone by assigning to its name property, and there we assign the new name. Furthermore, we do the same for the vertex group itself. Functionality-wise, this is all there is to it, but I want to point you to one more tiny little detail. You can see that I've used quite a bit of empty lines in my code, and what this does is that it groups logical bits of code together. So here you have a bit of code that determines the new name, and then here you have a bit of code that actually applies that new name. These are two separate things, and so I like to separate them with a new line. Don't be afraid to put a new line in your code every once in a while and make it extra readable. And this brings us to the end of the video. To recap, we've used print to report the progress of our script and to test that it's actually doing the right thing. We've looked at iterating over children of objects. We've been modifying bones and vertex groups. And we've looked at using empty lines to restructure the code a bit and make it even more readable. The next video will be about rendering objects from all sides. See you then. Hello and welcome to Scripting for Artists. My name is Sybren, and in this video we'll be looking at rendering an object from all angles. Well, all angles. Again, this video is about a question on Stack Exchange. Here Baku asks to render an object from many perspectives, and he explains it as having a sphere around the object and then rendering from the direction of each face. The accepted answer doesn't even use scripting, but uses an add-on to create a spiral curve and then constrain the camera to the curve, animate it, and then render the animation. Of course, this is a valid approach, and if it works for you, that's good, but we're going to take a slightly different tour and use scripting. So instead of using a spiral, we're going to use a mesh. So it's pretty close to the original question, except that instead of placing the camera at a face, we place the camera at a vertex. I thought that would be easier because a vertex is actually a concrete point in space, whereas with a face it's less clear where exactly the camera will be. Before we start scripting, we have to set up the camera and constraints. We have to set up the whole scene. So let's go to Blender. Here you have it. I've made a sphere which is shown in wireframe, and it has very little points, so it's not really sphere-like, but otherwise it would take too long to test our code. In the center of the sphere we have Suzanne, which will render, and we have a camera. The camera has a track 2 constraint to Suzanne, so that we can move it around and it will always point in the right direction. So now the only thing our script has to do is place the camera at the right point and hit render. So our approach is going to be to loop over all the vertices in our sphere mesh and then convert them from local coordinates to world coordinates. We'll see soon why. And then we can place the camera and render a frame. So again, let's start simple and look at looping over all the vertices first. So this is the start of our script. We import bpy as usual. We define two objects. We could have also taken them from bpy.data.objects, but sometimes it's nicer to take them from the scene rather than the global objects collection, and I just wanted to show you how that's done. Now we have to get to the vertices, and the vertices are defined on the mesh, and the mesh can be reached at placement.op.data as we've seen when we were rendering 10,000 OBJ files. Now instead of looping over them directly, we call enumerate and then pass the vertices there. And this does something special. It returns the vertices that are looped over, but it also returns their index. I've done this because I want to be able to say vertex 0 is at coordinate something, vertex 1 is at coordinate something, and then it's useful to have that number 0, 1, 2, 3, etc. run along with the actual vertex. So if you ever need to have a counter, as well as the objects that you're counting while you're looping over a collection, enumerate is the function to use. Okay, so now we have the vertex and we need to have its coordinates, which are stored in .co. So we can simply say vcoord equals vert.co. I wouldn't put a line like this in the code by itself. Usually I would just rather use vert.co directly, but we'll have to change this line later on, so that's why we'll keep it here. Once we have the index of the vertex and the coordinates of the vertex, we can construct a print statement so that we can see that it's actually working. And then there's another trick. We can set bpy.context.scene.cursor location to any location in 3D space, and it will put the 3D cursor on that spot. This is a very nice way to debug code because you can visually see that you're actually looking at the correct coordinates. This is much easier than comparing numerical coordinates all the time. And as usual, we end in a print done statement so that we know our script is done. Here we have the script in Blender. Let's run it and keep an eye on the 3D cursor. You saw it move. So right now it's actually at one of the vertices of the mesh, and it's pretty much spot on. Here we can see the output of the script in the terminal that I used to start Blender, and you can see I ran the script a couple of times. Right now our sphere is centered around the origin, it's not rotated, it's not scaled, so that makes for a pretty easy starting point for our script. But now let's see what happens when we start manipulating the object. We can scale and rotate it a bit, and of course it still has to work. So let's rerun the same script. Now you see that the 3D cursor is in the wrong position. Actually, it's still in the same position that it was before, with the unscaled, unrotated mesh. This is because the coordinates of the vertex are stored in a local coordinates, so it doesn't take into account the rotation and location and scaling of the actual object. So how do we solve this? Well, fortunately it's pretty easy. All it takes is a little bit of math. All the transformations of an object are stored in a matrix. You don't really have to understand how it works and what it contains. Just know that the matrix is one thing that contains the location, the rotation and the scale of an object. From the sphere object, we can get its matrix world property, and this matrix contains everything that we need, including transformations that came from animation, constraints, everything. If you take a matrix, put that on the left of a multiplication, and then on the right side you put the coordinates, this will convert from the local coordinates to the world coordinates, exactly the way we need. So let's get back to Blender and see how it works now. Here we have our edited code, and if I run it, you can see that the cursor is in the right position. Can rotate and scale it some more, and it will just keep working. So now we actually have all the ingredients that we need. We have the correct coordinates for the vertices, we can place the camera there and render a frame. So just as in Tech Video 2, where we rendered 10,000 OBJ files, we have to set the file name to render to. That is done here, and this time we have a slightly different construct because we have the index, and that's an integer. And we cannot just add an integer to a string. It would be the same as adding your age to your name. They're two different types that are not compatible. So instead we use string formatting. And it looks like this. You have a string with a special bit in here. And this special bit will be replaced by whatever you give to the format function. This means you want to have a decimal number here, and it needs to be 3 digits wide. And you want the number to be 0 padded, which means that you get vertex -000 for the first vertex, -001 for the second vertex, and so on. By 0 padding the numbers, the alphabetical ordering will also be the numerical ordering, which makes it easier to later go through all your rendered frames. Because rendering can take a while, I like to print that we're rendering and what we're rendering before the rendering starts so that I can see what it's doing. Furthermore, we set the camera's location, which you do by assigning the coordinates to the location property. And then again we tell Blender to render and save a frame. Again, the break command is there so that we can test for the first vertex only, and we can remove it once we've seen it works, and then re-execute the script to render from all vertex positions. And that's it. This is a working script. To recap, we have looked at placing the 3D cursor for testing. This is one of my favorite techniques to check that 3D coordinates I'm working with are actually in the correct spot. We've looked at how to iterate over vertices in a mesh, and we've also seen how to give a number to all these vertices while we're iterating over them. We've seen how to convert from local coordinates to world coordinates. And we've even looked a little bit at string formatting. I will put links to the documentation in the video description, because the string formatting is really powerful, but it's out of scope for this video to discuss all of that now. So this is the end of scripting for artists. I hope you've enjoyed it, and if you have any questions on any of the videos, please leave comments on the cloud. Please leave comments on the cloud. I will look at them, I will give you answers, and I hope we can turn this into a really nice interactive training series. Thank you for watching, and see you online.